Okay, so welcome to MathStat 343 probability. So I know a few people had told me that they were not feeling well and they're going to be watching this remotely. Okay. And so what I want to do today is I want to, again, talk a little bit about some of the properties of moment generating functions and all the different cousins related to them, talk about the Poisson, the normal example, and then I want to show the central limit theorem should be true for Poisson random variable. So it's going to be a proof modulo some results from complex analysis, but it should be enough of a sketch that you would be willing to accept these results. And if you truly care, you will now be motivated to take a real analysis or a complex analysis class later, or just watch the videos and talk to me. The big items, as always, is trying to find a path through the algebra. And so in some sense, today's lecture is really not necessary. We could just prove the central limit theorem in the general case. I think it's much better to do it twice. First, let's do it for a specific example that we can get our hands on that is really clear and easy to work with. And once we understand that case, then we'll say, oh, it's not that bad to just generalize this. Where do we have to change things? This is really good advice in general in life, is try to prove something in a simple case, build up some intuition, get a sense of how things are going. And as you're doing it, watch and see, where do I really need these nice properties? What do I really need? Is this important, or is it just making the proof a little bit easier? But as long as I have something else, I'm going to be fine. We will see that certain distributions are easier to work with than others. For example, if you have a nice closed form expression for your moment generating function, this is a good sign that this is a really good choice of a distribution to look at. We saw when we were looking at the Fibonacci numbers, we could form a generating function that had a closed form, and from that we could then get Benet's formula, an explicit formula for the nth Fibonacci number. Okay, so here is where we were last time. We had the moment generating function, and what we had with the moment generating function was that it is the expected value of e to the tx. So explicitly, if we have a discrete random variable taking on, say, integer values, it's the sum from negative infinity to infinity. If it's continuous, it's an integral e to the tx f of x dx. And again, it's not clear that these will converge for values of t other than 0. We know it will clearly converge at t equals 0 because it's a probability distribution, so its integral is 1, or its sum is 1. We saw that there is a real interplay between generating functions and moment generating functions. It's just a change of variable. So if we basically take the generating function and evaluate it e to the tx, we get the moment generating function. Or conversely, if we evaluate the moment generating function at the log of s, we get the generating function. What this means is essentially once you prove a result for generating functions, it essentially follows immediately from moment generating functions. If you want to, you can of course repeat the proof, there's no one stopping you, but the more efficient way is to just say, oh, wait, we proved it in this case, let me just now choose t to be. Now the only thing you have to be a little bit careful about is what kind of numbers could e to the t be as t ranges over real numbers? Positive, right? E to the t is never going to be 0, it's never going to be negative. So it is restricting a little bit of where you are evaluating the generating function. Okay. And we saw for the generating function, what was a really good place to evaluate it at? 0. Oh, we can't really evaluate it at 0 here. Okay, so that could be something worth noting. All right, so here was the big result I mentioned last time. So the first statement we already proved, and this justifies the name moment generating function, the function that gives you the moments. It has a Taylor series expansion where the coefficients are the uncentered moments. So if your distribution has mean 0, then there's no difference between the centered and the uncentered moments. What this tells us is that if we know the moment generating function, then by differentiating, or just by explicitly writing down the Taylor series expansion, we can calculate the moments trivially. This becomes another way to find the moments of a distribution. We did direct calculation, we did differentiating identities. Another way is to use the moment generating function and then Taylor expand it or take derivatives. The next one we haven't proved yet. I'm going to circle back to 2 in a second. The third one we basically already done. The moment generating function of a sum of independent random variables is the product of the moment generating functions. This is just inherited from the generating function result. And of course, it extends to sums of n terms. And you can see if we're going to be studying the central limit there for the distribution of a sum of n independent random variables, this is precisely what we would like to have. You know, it's a great tool. And so the real thing we need to prove is the second one. Well, we start off, so proof of two. So the generating function of x at t is the expected value of e to the tx. Let's let y equal alpha x plus beta. And the generating function y of t is just the expected value of e to the ty. So again, this is a follow your nose proof. You start off with the definition and you just unwind. Well, we know what y is. Y is just alpha x plus beta. So let's just plug it in. So this is just the expected value of e to the t alpha x plus beta. This is the same as the expected value of e to the t alpha x times e to the t beta. Okay. What can you tell me? This is the expected value. So this means I'm integrating this against f of x dx. What can you tell me about e to the t beta? Yeah, it's always e to the t beta. It's a constant. T is fixed. This is an integral with respect to x. You know, if you just go back one page, you know, the moment generating function is just the integral of e to the tx times f of x dx. I can just pull the e to the t beta outside. And so it's just e to the beta t, just writing it in reverse order, e to the t, whoops, to the e. And now I'm going to write it as alpha t times x. Okay. Well, the moment generating function of x is the expected value of e to the tx. When I say the moment generating function of x, that's a little bit vague. The moment generating function of x at the point t is the expected value of e to the tx. I have the expected value of e to the alpha t times x. Oh, well, that's just the moment generating function of x evaluated at alpha t rather than t. So we just get e to the beta t and then just the moment generating function x at alpha t. And that's the proof. So the proof really is a straightforward follow your nose, just keep substituting in. And at the end of the day, we have this beautiful, nice relationship that tells you if I do a nice linear change of variables, if I rescale x and add beta, this is how things change. So whenever you see a result like this, you know, one of the questions you should always ask is, who gives a damn, who gives a shit? Why do we care about this? Well, how might I want to rescale things? Maybe we rescale to have what? What might be a really good choice to rescale to make what happen? Yeah, to standardize. To have mean 0, standard deviation 1. That's why we're going to want to have things like alpha and beta. Is given a random variable, instead of looking at the sum, I might subtract something so it then has mean 0 and then adjust so that it has standard deviation 1. And this is just telling us how things transform. Okay. So the next theorem is an immediate corollary of something we've already had. It just says that if we have a discrete random variable, then the moment generating function is unique. And this is because the moment generating functions are just the generating functions, and we had the result for generating functions. We're really not going to use this too often. The reason this is valuable is if I'm trying to prove some kind of convergence, it would be nice to know if there's only one possible thing it could be. Sadly, sometimes there's more than one choice, and you have this terrible situation of there could be several different answers, and they all pass the same tests. How many people here have ever done clock arithmetic? Everyone's hand should be up. Or sometimes it's called modular arithmetic. If it's 9 o'clock now, what time is it in 6 hours? 3. So everybody has told me 9 plus 6 equals 3. On a clock, yes. On a clock, on a standard 12-hour clock, we can't distinguish between 3 and 15. And so in terms of the properties we're looking at, 3 and 15 behave the same. So a lot of times when we look at a lot of different distributions, depending on what test we're using, we may not be able to tell the difference. If we're only looking at certain properties, I can't distinguish. It would be wonderful to say, hey, if I know all the moments, I can distinguish the distribution. That's not the case. It's reasonable to say, well, what if I only know 2 moments? Do the distributions have to be the same? No. We know examples of distributions that differ at 2 moments. Can you find a distribution that agrees for, say, the first k moments and then disagrees after that? So make that extra credit. If I give you any k, can you come up with 2 distributions that agree for precisely the first k moments, but then disagree beyond that? Right. This just shows you how bad the world can be. So here are 2 probability distributions, and they have the same sequence of integer moments. So this is your example 19.6.6 in the textbook. And this just tells you the subject is bad. You have to be careful. You have to have some really good analytic machinery to handle stuff like this. Knowing the distribution of the moments is not enough. There's a great physics paper, Can You Hear the Shape of a Drum? If you know what kind of resonances it has, does that uniquely determine? And the answer is no. And so we have a similar thing here for probability. If you actually calculate these, you will see that they all have the same integer moments. If memory serves, it's been a while since I've done this. I think they also have the same half integer moments, but not beyond that. And then as you start calculating other moments, you see that they actually do differ. When you look at them, they clearly look different. Yet somehow everything matches up precisely, so they agree at infinitely many moments. And this is just a warning of just how bad things can be. Well, I can't talk about that without talking about my favorite counterexample function. The e to the negative 1 over x squared if x is not 0 and 0 otherwise. And if you look at a plot of this, it is so damn close to 0, near 0, it's indistinguishable. I mean, if you think about taking x to be 1 over 1,000, then you had e to the negative 1 over 1,000 squared, that's e to the negative million. It's a nice exercise to just try to get your hands on just how small e to the negative 1 million is. Mathematica is not even trying to plot anything here different than 0. Okay? And so this tells you, we talked about this with Taylor series. Taylor series are not unique. So the Taylor series is identically 0. As each derivative at 0 equals 0 by L'Hopital. And so again, this is just motivation for intellectual honesty. I am not going to prove the central limit theorem in full glory in an introduction to probability. We just don't have the technical machinery. We can prove it in some special cases, or at least make it very, very plausible. Okay. So now let's go back to Poisson random variables, because Poisson random variables are nice. They have a beautiful generating function in closed form. And so we have a couple of ways to try to find the mean and the standard deviation. If I can find the first moment and the second moment, well, once I know the first 2 moments, I can get the standard deviation. I just look at second moment minus first moment squared. That's the variance, take the square root. So because the moment generating function is just the sum, we can go back a few pages. So here is the moment generating function, just expanding things out. So if I just put this in here, if I want to calculate moments of the Poisson distribution, I just have to differentiate. If I differentiate once, I get mu1 prime, which is just the mean. If I differentiate twice, the t squared becomes 2 times t, then becomes 2 factorial. That cancels the 2 factorial down below, and I just get the second one. And then again, when I put in t equals 0, everything else cancels. If I want the third moment, I would differentiate 3 times, and only the coefficient of the t cubed term will survive. And because I have a 3 factorial down below, it's going to be canceled by the 3 factorial that comes down from differentiating. All right, so who would like to differentiate my moment generating function? Mx prime of t is what? We have an exponential of lambda e to the t minus 1. So how many of you remember Calc 1? How many of you at least remember you took it at some point? Okay. How many of you remember seeing just really strange functions because they wanted to test your ability to take derivatives of strange things? Here is an exponential of an exponential. And I actually care about this. This is not just me, trying to have fun with my students. I'm the professor. I can make you do whatever derivatives I want. It's on the exam. You've got to do it. This arises naturally. And there's other places where exponential arises naturally. If you look at things such as tossing a fair coin and what's the longest one of heads, you see exponential arising in something like that as well. So how would I take the derivative? What rule would I use to calculate the derivative e to the lambda e to the t minus 1? Chain rule. So we have an exponential. So it's going to just be the exponential e to the lambda e to the t minus 1. And then we have the derivative of that piece, right? So it is e to the lambda e to the t minus 1. And then what's the derivative of lambda e to the t minus 1? It will just be lambda e to the t, right? The minus 1, that's the same as lambda e to the t minus lambda, right? And so if we now take the value as we're all good on the derivative. So now when we take t equals 0, we get e to the lambda e to the 0 minus 1 times lambda e to the 0, which is just lambda. Okay. Now what do we do? I want to get the second derivative. What do I have to do? Take the derivative again. And what rule will I have to use now? Uses the product. It's what rule do you have to use first? I have to start off with a product rule. I have a product of two functions of t. And then for the derivative of the first one, I have to then use a chain, although fortunately I already know what the derivative of that is. Who's excited about doing a product rule this early in the morning? All right. So I'll let you do it and then just report back. So who wants to see how to avoid using the product rule? Well, so one possibility is we could try to multiply them together. And if we do, well, then you would have an e to the lambda e to the t minus 1 plus t, which is not too bad. So you could avoid it. So can avoid product. We just have mx prime of t is e to the lambda e to the t minus 1 plus t times lambda. There's another way to do the problem. Or the moment generating function at t is e to the lambda e to the t minus 1. This is the sum and goes from 0 to infinity of lambda to the n e to the t minus 1 to the n over n factorial. And what I want to do is I want to form a series expansion in terms of t. Well, unfortunately, e to the t has a series expansion itself. But e to the t starts off as 1 plus t. I subtract 1. So this is at least to the power t. Right? So if I just look at this, I'm going to get the n equals 0 term. So when I take n equals 0, I just get 1. Then I get the n equals 1 term. When I take n equals 1, I'm going to have lambda e to the t minus 1. Then I have 1/2 lambda squared e to the t minus 1 squared plus at least t cubed. So everything from this point onward is going to be at least t cubed, because e to the t minus 1 is at least t. Well, if I want to calculate the second derivative, if I want to calculate the second moment, I only need to get up to t squared. Do I have to worry about any of these terms? So I just get 1 plus lambda e to the t minus 1. That's just going to be 1 plus t squared over 2 plus dot 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 minus 1. I don't need to go beyond t squared, right? The next piece would be plus lambda squared over 2. And now I have e to the t minus 1 squared. So it's 1 plus t squared over 2 plus dot 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 minus 1 squared plus dot dot dot. So when I look at this, I get 1. Now the 1 minus 1 cancels, so I'm going to get lambda t. And then I'm going to have t squared over 2 times lambda, so lambda over 2 t squared. For the next piece, I have a lambda squared over 2. The 1's cancel, and now I'm left with a t plus t squared over 2 squared. When I square that, I only care about things that are of size t squared. T cubed and higher doesn't matter. So do we agree that the t squared term doesn't matter because when I square it, if it hits itself or hits the t, it's going to be too high? I only care about the t term. And so I'm going to get plus lambda squared over 2 times t squared. So I get 1 plus lambda t plus lambda squared plus lambda over 2 t squared. So the coefficient of t squared over 2 factorial is the second moment. So second moment is just going to be lambda squared plus lambda. So the variance is lambda squared plus lambda minus the mean squared, which is just lambda. So the variance of the Poisson is equal to lambda. So if I've done the calculation correctly, this is what we get. So there's many different ways to do this. If you're comfortable doing this algebra, you're essentially bypassing taking derivatives. As an aside, how bad would it be to take the derivative? So we had here was what we had. And so we just try to take the derivative again, we would get mx double prime of t would be lambda e to the lambda e to the t minus 1 plus t times, now we need the derivative of lambda e to the t minus 1. Oh, I'm sorry, the one is not in the x, right? Minus 1 plus t derivative. So the lambda e to the lambda e to the t minus 1 plus t. And then the derivative of this would become lambda e to the t plus 1. So the second derivative at 0 would become lambda e to the lambda e to the 0 minus 1 plus 0 times lambda e to the 0 plus 1. E to the 0 minus 1 is 0, so we have e to the 0 lambda, which is just 1. So we get that this is equal to lambda times lambda plus 1 is lambda squared plus lambda, which fortunately is what we got a moment ago, and math is consistent. So again, many different ways of doing the algebra. Whichever way you're comfortable with, that's fine. So we now know if you have a Poisson with parameter lambda, the mean is lambda, the variance is lambda, the standard deviation is the square root of lambda. And we just saw other ways of doing the algebra. Okay, any questions on these calculations? Okay, so the next is we really need the moment generating function of the standard normal. Given that we're trying to use the moment generating functions, what we want to do is basically say, imagine we have sums of independent identically distributed random variables. Let's calculate the moment generating functions of the sums. And imagine that we see that these moment generating functions are converging to the moment generating function of the normal. Well, if they're converging to the moment generating function of the normal, hopefully that means the densities also are converging to the density of the normal. That if my moment generating function is converging to your moment generating function, then my density is converging to your density. That's not always the case, but it is the case when things are nice. So we need to know what is the moment generating function of the standard normal. Now, if my density is converging to yours, is it possible that my moment generating function is not converging to your moment generating function? No. If my density is converging to yours, then the moment generating functions have to be the same. So this is a necessary condition. The question is, when is it sufficient? So we'll say X is a normal with mean 0, variance 1. You can do the more general case. And so we want to calculate the moment generating function of X, which is the expected value of e to the tx, which is just the integral from negative infinity to infinity of e to the tx, 1 over square root of 2 pi e to the negative x squared over 2 dx. I have deliberately not watched or prepared for this lecture. This is another one where it's just follow your nose. Right? Does anybody know how we're going to handle this integral, the technique we're going to use? Famous technique, you've seen it in Algebra 1, Algebra 2. We're just trying to solve certain things. E to the negative, nope, negative 1/2 x squared plus 2x. Complete the square. Excellent. Right? And so how do you complete the square? Bring it home. T squared minus t squared. So complete the square by doing nothing. Well, we have an e to the negative x squared over 2. We have an e to the tx. Oh, wait, should that be a negative 2? Oh, that should be a negative 2, right? We have an e to the tx. We have an e to the negative x squared over 2. I want to just have a common exponential. So if I multiply, I have e to the negative 1/2 x squared. Good. I have e to the negative 1/2 times negative 2 e. I dropped the x. That's why you're confused. I dropped the x. So x squared minus 2tx. All right. So with the correct math, does it make more sense? Okay. So with the x there, now it should make sense. I'm sorry? Nope. Because now this is set up. So now we'll get 1 over square root of 2 pi, integral from minus infinity to infinity, e to the negative 1/2, and we have x minus t squared minus t squared dx. And so now this is just 1 over square root of 2 pi, integral from minus infinity to infinity, e to the negative 1/2 x minus t squared, and we'll have e to the t squared over 2 dx. Well, I can pull the e to the t squared outside of the integral. And so this is just e to the t squared over 2, integral minus infinity to infinity, 1 over square root of 2 pi, e to the negative x minus t squared over 2 dx. Oh, this is the integral of a normal with mean t and variance 1. So what is this integral equal to? Yeah. So this is just e to the t squared over 2. So here is the moment generating function of the standard normal. It's just e to the t squared over 2. Okay. So now it's time to prove the central limit theorem, at least in the special case of Poisson random variables, modulo some big results from analysis that we will not prove in this class. But if you're interested, I have some videos and I'm happy to chat about what needs to be done. So here is the Poisson random variable. It has mean lambda and variance lambda, standard deviation square root of lambda. So let's let x be x1 plus xn. Each xk will be Poisson with parameter 1. So x will be Poisson with parameter n. So there's many ways to see this. One is we've shown before that Poisson plus Poisson is Poisson, and you just add the parameters. We could also say the moment generating function of x at t is just the product, k equals 1 to n, of the moment generating function of each x k of t. But all those moment generating functions are the same. So it's just, might as well use the first one at t to the nth power. And so that would just be e to the 1 times e to the t minus 1 to the n, which is just e to the n, e to the t minus 1. So just exactly as we claimed. And again, we didn't have to go through the product here. I'm just doing that because later it's going to be more convenient to work with the product. And then we're viewing this as raising something to the nth power. We really don't want to study x. We want to study the standardization. So we want to standardize. So let's let z be x minus the mean of x divided by the standard deviation of x. Right? What's the mean of z going to be? We take x, we subtract x's mean, and then we divide by the standard deviation of x. Its mean is going to be 0. And what's the standard deviation of z going to be? 1. So the whole point is we want to compare to the standard normal. And so rather than having something that has growing variance or possibly even a growing mean, I might as well just adjust things to have mean 0 and variance 1. Well, what is the mean of x? So it's Poisson random variable with parameter n. What does its mean? N. And what is its standard deviation? Not n. Square root of n. So I'm going to write this as 1 over root n times x minus root n. Anybody know why I want to write it like this? The calculation will be easier. Does this remind you of anything we've seen earlier today? Let's visit some earlier slides. Rewind. The moment, I just exploded a little. The moment generating function of alpha x plus beta is e to the beta t times the moment generating function of x of t. Right? foreshadowing. So we use with alpha equals 1 over square root of n and beta equals negative square root of n. So we get the moment generating function z of t is going to be e to the beta t, so it's going to be e to the negative square root of nt. The moment generating function of x at alpha t, alpha is 1 over root n, so it's going to be t over square root of n, right? So it's e to the negative root nt, and then the moment generating function of x was e to the n, e to the t minus 1. Right? So it'll just be e to the n, e to the t over square root of n minus 1. And if you look at that, doesn't that look a lot like e to the t squared over 2 as n goes to infinity? Yeah. All right, so we need to do some algebra with this. Does anybody have an idea what our first algebraic step should be? Change variables. Okay, how? So we have to deal with this expression now. So the question is, how should we start doing the algebra? Any thoughts? So we have this product, e to the negative root nt, e to the nt, e to the t over square root of n minus 1. How might we try to deal with this product? What would we try to do? I'm asking you how to take a log, right? When in doubt, whenever you hear the word product in this class, just yell out log. Okay? Well, if you want, even yell out log before I ask about a product and expectation. Right? Take the log of the moment generating function z. But when we take the log of a product is the sum of the logs. What's the log of e to the negative root nt? That's just negative root nt plus n times e to the t over root n minus 1. All right, now let's just start expanding things. Now, I'm a little bit worried about the e of the negative square root of nt because as t is fixed and n goes to infinity, this is going to diverge. I hope that this term is going to cancel that. Now, if you look, I have an n. Oh, n is much bigger than square root of n. And I have a t over square root of n. So maybe the square root of n and the n reinforced in such a way that everything works out nicely. So now let's start expanding. This is 1 plus t over root n plus 1 over 2 factorial t over root n squared plus 1 over 3 factorial t over root n cubed plus dot 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 minus 1. I'm just expanding out e to the t over square root of n. You can see now how nice it is that we have a closed form expression for the moment generating function. Because we have a closed form expression for the moment generating function, I can do this. The only difference between what we're doing now and the proof in general is that we have, in the general case, we don't have anything as nice as this. So we have to then just do a generic expansion of the moment generating function in terms of its Taylor coefficients. And that just makes the algebra a little bit worse, which is why we will have a break and do a fun topic on Friday, because there's only just so many days in a row of calculations like this that you can do. So now when we start expanding, the 1 and the -1 cancel. Good, because that n is much larger than the square root of n. The next is going to have a t over root n times n. That becomes the t square roots of n, which perfectly cancels with a -√nt. Okay. Then we have a 1 over 2 factorial t squared over n times n. Oh, that's just going to be a t squared over 2. The next piece is going to be t cubed over n to the 1.5. I multiply by n, so I'm going to have plus 1 over 3 factorial t cubed over square root of n. The next would be plus 1 over 4 factorial t to the 4th over n, plus 1 over 5 factorial t to the 5th over n root n. As n goes to infinity, goes to 0. And that's the whole point, is t is fixed. So because t is fixed, as n gets very, very large, all of these things are going to be decaying. And so we get that as n goes to infinity, the log of the moment generating function z of t converges to t squared over 2. So if we exponentiate, we get the moment generating function of z converges to e to the t squared over 2. Oh, and what function has the moment generating function e to the t squared over 2? This is the moment generating function of the standard moment. So this is an almost proof in this case of a Poisson random variable. We've shown that the moment generating function is convergent. And in fact, we can quantify the rate of convergence by looking at these terms over here. The miracle of the central limit theorem is that all of these distributions doesn't really matter. The sum of independent, identically distributed, nice random variables converges to being normally distributed. That seems a little bit surprising that it doesn't really matter what distribution I use. I get this central thing back. Well, if I give you any distribution, I can always standardize it and adjust it to have mean 0, variance 1. The first moment of your distribution that really is meaningful about its shape is the third moment, or the fourth moment if your distribution is symmetric about the origin. And in fact, that's going to control the rate of convergence. So the higher moments converge, so the higher moments control how fast you converge to the standard norm. That's where the shape of the distribution matters. But the universality of the central limit theorem comes from the fact that, look, I can always adjust if my variables are nice to be mean 0, variance 1. That's why you have this universality, because the first two moments don't really show up in the analysis. It's only the third moment that shows up, and it shows up as an error term tending to 0. So just a couple of results. Standardizing, we've already talked about this. If I give you a random variable, you subtract off its mean, divide by its standard deviation, and that now gives you something with mean 0 and variance 1, which is much easier to analyze. The next is the moment generating function of a Gaussian in general is e to the mu t plus sigma squared t squared over 2. We're really only going to use the special case when the moment generating function is that of a standard number, e to the t squared over 2. This is just extremely important. The big results that we're going to use without proof is that assume the moment generating functions exist in the neighborhood of 0. If the moment generating functions are equal, then the densities, or actually the cumulative distribution functions, are equal. And so that then basically gives us the densities are equal. So again, if everything is nice, if the moment generating functions exist in the neighborhood, then you can go from the moment generating functions being equal to the densities are equal. And then the next one is if we have a sequence of random variables with moment generating functions mxi, and in the limit, the moment generating functions converge to the moment generating functions of something nice, and everything converges in some neighborhood, then the densities have to converge, or at least the cumulative distribution functions have to converge. So this is the big result that we're going to just appeal to from complex analysis. That if the moment generating functions exist and converge, then that means that the densities also converge. Okay. So I don't think I brought this before, but I forgot to bring this. This is a truncated Cauchy distribution that one of my students gave me years ago. Why is this such a, nothing personal, why is this such a bad distribution? Yeah, there's no mean to speak of. I mean, you can at least, you get into heated arguments about whether or not the mean exists. But once you get to the variance, there's no reasonable argument anymore. The variance is infinite. So clearly, we're not going to be able to calculate a moment generating function for the standard Cauchy distribution. So the problem is when we study things like the moment generating function of x is the expected value of e to the tx, doesn't always exist. It is much easier to study objects that exist than objects that do not exist. There is a trick. You study the characteristic function. And I think they often use, phi x of t. And you're going to say, really, Miller, this is what you're doing? E to the itx, where I is or I am the square root of -1. This makes a big difference. Yes. This makes a tremendous difference because now, if you look at what you have integral minus infinity to infinity e to the itx, and then the density f of x dx, where e to the itx is cosine tx plus I sine tx. The absolute value of e to the itx equals 1. Because the absolute value of a complex number is the square root of the sum of the squares of its components. So if I try to look at this, well, this is absolute value of 1. This is non-negative. So if I look at the absolute value at any point, this is going to be less than or equal to the integral from minus infinity to infinity, absolute value of e to the itx times fx of x dx, which is just 1. So this integral always makes sense. It's always well defined. And so it turns out if you shift to the complex plane, a lot of these calculations become significantly easier. So we are not going to do too much with this, but it's worth just being aware, what do you need to do to make the subject rigorous? There's a beautiful statement, oftentimes the shortest path to a theorem about real numbers is through the complex plane. Complex analysis just has a huge amount of tremendously powerful results that we can use to attack problems like this. And so when we have all these conditions, if the generating function, the moment generating function exists, well, they don't always exist, but the characteristic function does exist. All right, so the last one, I think I had some slides on this later, the change of base formula for logarithms. So the log base b of x equals y means x equals b to the y. And you can prove that the log of a product is the sum of the logs, all these different great results. The change of basis formula is the log of x base b is the same as the log of x base c over the log of b base c. So only need to know logs in one base. This is tremendously valuable. Less valuable now with computers, but in the old days when you were actually computing log tables, it was wonderful to only have to prove things in one base. So if the log base b of x equals, say, y, that means x equals b to the y. Now, we can also study what is the log base c of x. If we call that w1, that means x equals c to the w1. If we look at the log base b of c, we call that w2, that means b equals c to the w2. As x equals b to the y, this is c to the w2 to the y, right? but x is just c to the w1. So w2y equals w1. So y equals w1 over w2, but y is the log of x base b, w1 is the log of x base c, and w2 is the log of b base c. So this is quick proof of the change of basis formula. And the reason I wanted to get to this today is because we're talking about standardizing, and this is just a great example of it's enough to just do logarithms and numbers. All right, so this is a good place to stop for the day.